Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss the equation of motion for vortex flow. In our previous lecture, already we have discussed the concept of vortex flow and the types of vortex flow. We have seen in the previous lecture that vortex flow is of two types. One is free and another one is forced. So here we'll discuss about only the equation of motion for vortex flow. To derive this equation, here I have taken a fluid element which is rotating. And in this picture we cannot understand anything that which is fluid and which is the fluid element and how it is rotating. So for that, let me tell you. So there is a container is there, suppose, and in this container we have some water is there. Okay, there is some level of water is present in this container, and let's draw the center line of this water container. And here I have taken a fluid element which is, suppose, when it started rotating, there is a fluid element what I have taken. Suppose this is the fluid element is there in this, and from this center point or from the center line of this fluid, the distance of this from the center line to this fluid element with a radius of r. Okay, and this fluid element what we have taken when it started rotation. Okay, and so the same thing is considered here. So this is the fluid element, and the fluid element rotating in this path. Okay, and see, this is the path only. The fluid element is this one, A, B, C, D. This is the fluid element what we have taken here, and the distance from this center point, let's suppose O. This is the suppose O point. So O point to this fluid element, how much distance is there? That is r, the radius of this fluid element, or you can say the distance from the center point to the fluid element, that is r. Okay, so here the fluid element what is there? Now ABCD is the fluid element what we have considered. So let's write this. ABCD is the fluid element what I have considered, that is rotating at a uniform velocity. Okay, this is rotating with a uniform velocity v, okay, in a horizontal plane. So these things we have considered in a horizontal plane, keep in mind, about an axis. So this is the axis line, and that is perpendicular to the plane. Okay, and passing through a point of O. This is the point O. Through this point it is passing. Okay, now here few terms are there. Let me tell you. One is r. So r is the radius of the element, okay, from the O point, from the center point O. So radius r equal to radius of the element. Which element? Now this element A, B, C, D, that fluid element, that is this part. Okay, the distance of this. Now next is next term is delta theta. So delta theta is the angle subtended by the element. This element made an angle of delta theta, this one, okay, at O point. With respect to O point, this fluid element made an angle, that is delta theta. So next is, we can consider delta r. So delta r is actually the radius thickness, this one. If you consider this, distance of this from one layer to another layer, see, this is the delta r. Okay, so delta r is the radial thickness of the fluid element. Radial thickness of the fluid element. And next is delta A. Delta A is the nothing but the area of the cross section. The area of the cross section of the fluid element, what we have considered here. Okay, these are the terms we need to consider. Now when it started rotating, or when this fluid element was started rotation, here some kind of forces are acting. The forces is going to act on the fluid element. Okay, so what kind of forces are going to act on this fluid element? Now how we can solve this one, we'll see. Now we know that we can write the pressure equal to the force per area. Okay, and similarly we can write the force equal to pressure into area. Okay, this is the formula we know already from our school level. Now the forces which are acting on this fluid element, let me tell you one by one. First one, I can consider the pressure force One is the pressure force which is acting on AB surface. See, in this ABCD fluid element, we have two different surfaces, like one is AB, another one is DC or CD, we can say. So this one we can say one pressure force which is acting from this, this from in this side, inside part of this, that is PDA. PDA is nothing but the pressure which is acting on this fluid element, and delta A is the, as I told you, that is the cross sectional area of this small element. Okay, so this one I can write the pressure force which is acting on this side AB. So pressure force which is acting on this side AB, you can write that is P into delta A. So here it is area, normal area, and this is the small area of this particular fluid element. Okay, so that is the pressure force on the face AB, P into delta A. Second one we can consider similarly the pressure force which is acting on the opposite side of this AB, that is CD side. So at CD side, what we can consider? Now the pressure which is already acting on this, along with that some more pressure which will be existing in this zone of this fluid. So that can be considered suppose we can consider that is P plus some delta P will be there. Okay, so here suppose 5 bar pressure is there, in this zone again some 2 or 3 bar pressure is there. So both adding will get the pressure at this other surface of that. Okay, so that is P plus dP. So this dP or delta P we can write. So see, in this zone, if you see at this zone, at this fluid element zone, we have number of layers of fluid elements are there. Correct. So each layers we have some pressure is acting on that. Okay, if you take this layer, all this layer, we have some pressure which is acting, that is we can consider delta P or del P. And the distance, what is the distance of this? Now each distance we can consider del R. So the pressure force which is acting on that particular area or this zone, we can write del P by del R into delta R. Delta R is the total distance covered or thickness of this fluid element. So we can write this one, the pressure force on the surface CD, we can write that is already P is there, and this delta P we can write del P by del R into delta R whole bracket delta A, because delta is the cross sectional area. This is the pressure force, or this is the pressure, and this is the area. These are the two forces, correct? Another force is there, that is centrifugal force. Okay, the centrifugal force which is acting from the center of this point, when we already know about the centrifugal force, which is the impact of center and how it is rotating. Based on the rotation of this fluid element, we can consider the centrifugal force. So the centrifugal force we can write that is mv square by r, and which is acting in the direction that is away from the center. We know that when it is rotating, so that will be away from the center. Okay, and now we can start solving this one. Okay, so before solving, let's find out what is the mass of this, because it is mv square by r. For this we required the mass of the fluid element. So to find out this mass of the fluid element, first let me tell you one more equation is there. We know that density, the mass density equal to, we can write the mass of the fluid element by mass by volume. Correct. So mass equal to what we can write? The mass equal to, we can write rho into V, volume. Okay. Now the same thing I can write here. The mass of the fluid element equal to, I can write mass density into volume. Now, so what about the density of this? Let density rho into the volume of the object. I can write delta A, and the area into the thickness. Thickness is that nothing but delta R. Delta R is the area into thickness, I can write. So this one I can give a, suppose you can mention a equation 1. Similarly, we got the mass of the element. So just put this value in the centrifugal force. So we can write the centrifugal force, we can write this value, mass value rho delta A into delta R into V square by 2. This is equation 2, suppose. Okay, so this is the centrifugal force. Now let equating all these forces and what will get in the radial direction. So this is one equation, this is one equation, and this is one equation. See, this is one, and second one this, and third one this. Let's equalize these three equations in the direction of radial direction. So what will get here? So let's write second equation, P plus del P by del R delta R into delta A. Okay, this is the direction of this. Okay, now this is opposite direction to this one. So this minus, okay, P dA, P delta A. Okay, these are the pressure force. Okay, equal to, we can write the centrifugal force. So centrifugal force, what we got here? We got rho delta A delta R into V square by 2. Okay, now here if you solve this one, we can get P delta A, P delta A. This P delta A, P delta A will be cancelled. So what will get here? Del P by del R delta R into delta A equal to rho into delta A delta R V square by 2. So this is the equation we are going to get in this point. Now delta R delta A, you can see delta R delta A, also we can cancel this, and finally what we are going to get, delta P by delta R equal to rho V square by 2. Rho V square by 2 is there. Yeah, mv square by R, not 2 actually. This is R. That's what I'm thinking, where this 2 came. So this is the equation what we got. Delta P by delta R equal to rho V square by R. So now this is another equation, we can mark it. Okay. Now at this point, if you see this equation, delta P by delta R equal to rho V square by R. Now here this pressure variation what we are getting, that is along the radial direction. This pressure variation what we are getting, that is along the radial direction. It may be for the force one or maybe for the free vertex flow. Okay. So this delta P by delta R actually, this delta P by delta R actually, it is called pressure gradient. This is known as pressure gradient. Okay. And here if you see the delta P by delta R is in positive. We got this positive equation, correct? Now this positive, positive value, you can see here, if P, the P value increases, as the radius will be increased. As this radius will be increased, the P value also will be increased. This is only for all these things, only for what? For only the horizontal plane or horizontal directions. Okay. Now if you consider for the vertical direction, if you consider next for the vertical direction, what will happen? Now vertical direction we have seen previously during the hydrostatic law, the pressure value. So there the pressure equation we got actually del P by del Z equal to minus rho into G. This is the equation actually during the hydrostatic law time. Okay. So now we can write this here, the Z equal to, that is the vertical vertical distance in the upward direction. Okay. Now this pressure, if you see, the pressure is varies, this pressure will be varies with respect to R and Z. Okay. This pressure will be varies with respect to, R and Z, because radial direction R and Z is the vertical direction. Correct. Now or you can say the P is the function of, you can write P is the function of R and Z. Okay. So now you can write the derivative of this pressure. If you able to write this derivative of pressure, then we can find out this equation. So what I'll write, so dP equal to, let me write in this way, del P by del R into dr. In terms of R I have written. Okay. Next, in terms of Z I'll write del P by del Z into dz. Okay. The same thing just I have written in this R form and Z form. Now already we got this value. See, this is the value of del P by del Z in this vertically, when the fluid is in the vertical. This is came from the hydrostatic law. Okay. And del P by del R already we have found here. Correct. Del P by del R already we found rho B square by R. So now just put this value, both of this value in this equation. So what we are going to get here? So we'll get dP equal to rho V square by R into dr plus, now this is minus, plus of minus will come. So write down like this, minus of rho G and this is dz. So finally we can write dP equal to rho V square R dr minus rho G delta Z. This is the equation we are going to get. Now this equation actually, it gives the pressure variation, the variation of pressure, okay, of a rotating fluid in any plane. Because if you see, we have taken the vertical plane and previously we have taken this is the concept of horizontal plane. Now this equation, if you this equation we can write for the vertical as well as for the horizontal plane. This one, another equation you can give. This is third equation gone. So this one, this is another equation you can write, equation of 4, and this one we can give equation of 5. Okay. So these are the equation, and this is the final one what we got here. So this is the pressure variation of the fluid element when it is rotating, when rotating in the vertically as well as the horizontally. So I hope you understand what the equation of motion for the vortex flow. If you are having any kind of doubt regarding this, you can give a comment on the comment box. Thank you all.